Two groups of scientists, using two completely different methods, both trying to measure the exact same number, keep getting two different answers. Not slightly different, not within the margin of error. Different enough that, after more than a decade of trying to make the discrepancy go away, the world's most advanced space telescope was specifically deployed to settle it. And instead, it made the disagreement worse. The number in question is called the Hubble Constant. It tells you how fast the universe is expanding, right now, at every point in space. It sounds like the kind of thing that should have one settled value. It doesn't. And the reason it doesn't might be one of the most important open questions in physics today, bigger in a lot of ways than any single alien signal headline, because if this discrepancy doesn't resolve, it means something is fundamentally missing from our model of the entire universe. This isn't speculation. This is a real, ongoing, name-attached scientific dispute, playing out in published papers between some of the most respected observational astronomers alive. It's called the Hubble Tension. And by the end of this video, you're going to understand exactly why physicists are using words like crisis to describe it. Here's the basic idea, stripped down. In 1929, Edwin Hubble discovered that distant galaxies are all moving away from us, and the farther away a galaxy is, the faster it's receding. That relationship, distance versus speed, gives you a single number called the Hubble Constant, usually written as h0, measured in kilometers per second per megaparsec. It's essentially the expansion rate of the universe encoded in one figure. It's worth sitting with how strange that idea already is before we even get to the controversy. A galaxy sitting 1 megaparsec away, roughly 3.25 million light years, is, on average, receding from us at whatever h0 turns out to be. A galaxy twice as far away recedes twice as fast. This isn't galaxies flying through space the way a rocket flies through the air. It's the space between them stretching, carrying the galaxies along with it. Get the value of h0 wrong, even slightly, and every distance calculation built on top of it. The size of the observable universe, the age of the cosmos, the mass of galaxy clusters, the timeline of when the first stars formed, shifts along with it. That's why a disagreement that sounds like a rounding error, 73 versus 67, actually cascades into some of the biggest open questions in the field. There are two fundamentally different ways to measure it, and that's where the trouble starts. The first method looks at the nearby universe directly. Astronomers measure the distance to relatively close galaxies using a chain of overlapping techniques called the cosmic distance ladder, starting with parallax measurements of nearby stars, calibrated by the European Space Agency's Gaia satellite, then stepping outward using pulsating stars called Cepheid variables, whose brightness rises and falls in a rhythm tightly linked to their true luminosity, a relationship discovered by astronomer Henrietta Leavitt back in 1912. From there, the ladder extends further using exploding stars called Type Ia supernovae, which detonate with such consistent brightness that they function as reliable, standard candles, visible across enormous distances. Chain all of that together, measure how fast those distant supernova host galaxies are actually receding, and you get a direct local measurement of h0. The team that's spent the most time refining this method is called JWST, the supernova h0 for the equation of state collaboration, led by Nobel laureate Adam Riess. Their most precise result, built from decades of Hubble Space Telescope data on more than 40 local supernovae, lands at 73, 0 kilometers per second per megaparsec, with an uncertainty of about 1 kilometer per second per megaparsec either way. The second method doesn't look at nearby galaxies at all. It looks all the way back to the cosmic microwave background, the faint, ancient afterglow of radiation left over from roughly 380,000 years after the Big Bang, when the universe first became transparent enough for light to travel freely. The European Space Agency's Planck satellite mapped this background radiation across the entire sky in extraordinary detail, and from the pattern of tiny temperature fluctuations baked into it, cosmologists can calculate what the expansion rate should be today by running the standard cosmological model, called lambda CDM, forward across nearly 14 billion years of cosmic history. That prediction comes out to 67, 4 kilometers per second per megaparsec, with an uncertainty of about half a kilometer per second per megaparsec. Read those two numbers again. 73, 0 from the local direct measurement. 67, 4 from the early universe prediction. Both methods are precise. Both have been refined for years by extremely careful, competitive teams who would each love nothing more than to be the ones who prove the other side made a mistake. And the gap between them isn't shrinking as the data gets better. It's holding steady, and by some analyses, getting statistically harder to explain away, currently sitting above 5 standard deviations of significance, a level of statistical confidence that, in most areas of physics, is treated as essentially confirmed rather than a fluke. For years, the leading explanation for the discrepancy was almost embarrassingly mundane: crowding. Cepheid variable stars are useful because they're bright and their brightness pulses in a predictable rhythm, but in a crowded, distant galaxy, a single Cepheid can visually blend together with nearby stars in Hubble Space Telescope images, contaminating the brightness measurement and throwing off the whole distance calculation. If that contamination was systematically biasing the local measurement, it could, in principle, explain away the entire tension without needing any new physics at all. James Webb was specifically positioned to test this because its infrared vision offers roughly 2.5 times sharper resolution than Hubble for exactly this kind of measurement, cutting through the crowding problem that limited its predecessor. It's worth understanding why crowding was taken so seriously as a candidate explanation, rather than dismissed early on. Cepheid variables aren't rare. Isolated objects sitting alone in the sky, they're found inside the crowded spiral arms of distant galaxies, often surrounded by thousands of other stars, packed into the same small patch of sky as seen from Earth. Hubble's optical resolution, while groundbreaking for its era, sometimes couldn't fully separate a target Cepheid from a nearby red giant or another unrelated star sitting almost exactly along the same line of sight. If even a small fraction of that contaminating light was being folded into the brightness measurements used to calculate distance, it could introduce a systematic bias that grew worse with distance. Precisely the kind of subtle, hard-to-catch error that could produce an artificial gap between local and early universe measurements without anyone noticing for years. That's what made it such an attractive explanation. It didn't require any new physics, just an underappreciated technical limitation of the older telescope. Rees and the JWST team ran the test directly, comparing more than 1,000 Cepheids measured by both Hubble and Webb across the same host galaxies, at the same wavelengths, anchored to the same geometric reference point, a nearby galaxy called NGC 4258, whose distance is independently known through the geometry of gas orbiting its central black hole. The agreement between the two telescopes' measurements came out essentially exact, a difference of about 1/100th of a magnitude, well within the noise. In a follow-up analysis, published with even higher statistical power, the team was able to rule out crowding as an explanation for the tension at 8 standard deviations of confidence. 8 sigma is not a marginal result. It's about as close to case closed as observational astronomy gets. That should have been the end of the story. If the answer had turned out to be crowding, resolving it would have meant the whole controversy was a subtle measurement artifact, and both numbers would have quietly converged. Instead, the opposite happened. Webb didn't shrink the gap. It confirmed the local measurement was solid, which meant the discrepancy was real and needed a real explanation. Not every astronomer initially agreed the tension was as bulletproof as the JWST result suggested, and one of the most respected skeptics was Wendy Friedman, a cosmologist whose own earlier work using the Hubble Space Telescope had itself helped establish the modern value of H0 in the first place. Friedman had spent much of the 1990s and 2000s as one of the leading figures in exactly this kind of measurement, and her team's skepticism about the tension carried real weight in the field precisely because she wasn't an outsider questioning the method. She'd helped build it. Her team's argument was straightforward and, on its face, reasonable. Relying on Cepheids alone might still carry subtle, uncorrected biases, whether from interstellar dust dimming their light unevenly or residual contamination from neighboring stars that even Webb's sharper resolution couldn't fully eliminate. The way to test that, her team argued, was to stop leaning on a single type of star and instead cross-check the distance ladder using entirely different stellar populations that would be affected by dust and crowding in different ways. Using JWST, the CCHP team measured distances to 10 nearby galaxies that had each hosted a Type Ia supernova, using 3 independent stellar distance indicators: Cepheids, a technique called the tip of the red giant branch, which uses the well-defined maximum brightness that aging red giant stars reach before a sudden internal shift dims them, and a newer method built around carbon-rich stars in a specific evolutionary phase, sometimes called the J-region asymptotic giant branch method. Here's where the story gets genuinely strange, in a way that even most people following the Hubble tension casually don't know about. The 3 methods didn't agree with each other. The tip of the red giant branch and carbon star measurements from Friedman's team came out lower, closer to the Planck prediction, actually easing the tension somewhat. But the Cepheid measurement from that exact same data set, using that exact same telescope on that exact same set of galaxies, came out at 72.04 kilometers per second per megaparsec, closely matching Rees's higher number and refusing to agree with the other 2 methods sitting right next to it in the same analysis. Averaged together, the 4 methods across both teams land around 70 kilometers per second per megaparsec, splitting the difference, but not in a way that satisfies anybody, because it isn't a resolution. It's 4 independent measurements that don't fully agree with each other, using the best instrument ever built specifically to settle the question. One prominent astronomer, reflecting on the tension in a 2023 review, put the mood of the field bluntly. After 2 decades of actively searching for cracks in the standard cosmological model, finding one this real leaves researchers wishing they could put the discovery back where it came from. What made the CCHP result so unsettling to the field wasn't just that the methods disagreed. It's that nobody could point to an obvious reason why the Cepheid measurement, specifically, kept landing high, while the other 2 indicators, measured in the exact same galaxies with the exact same telescope, landed lower. If Cepheids were the problem, some systematic flaw specific to pulsating variable stars, it should have shown up as an anomaly relative to red giants and carbon stars, regardless of which team was doing the measuring. And it did, but in a way that mirrored, rather than resolved, the original JWST result. That's the detail that kept the tension alive even after Friedman's team set out, specifically hoping to dissolve it. 2 teams that started from different assumptions, using different combinations of methods, kept bumping into the same higher Cepheid-based number, no matter how they approached it. This is where the story becomes genuinely current. In April 2026, a large international collaboration called the H0 Distance Network released what's being described as the most precise local measurement of the Hubble Constant ever produced, built specifically to avoid the earlier disagreement between methods by combining Cepheids, red giant branch stars, and carbon stars together into a single unified distance network, rather than treating them as separate competing measurements. The logic behind this approach is worth explaining, because it's a genuinely clever piece of scientific engineering, rather than just throwing more telescope time at the problem. Instead of picking one distance indicator and defending it, or running several indicators separately and hoping they agree, the network approach ties every method to the same galaxies wherever possible, cross-checking each star's distance estimate against the others within the same host, and propagating the uncertainties from every step together rather than treating each method's error bars as independent. If a subtle bias were hiding in just one technique, dust extinction quietly skewing the Cepheids, say, or metallicity effects subtly shifting the carbon stars, a tightly interlinked network like this is specifically designed to expose that mismatch rather than average it away. The team drew on data from Hubble, Webb, and the Keck Observatory in Hawaii, and pushed the total sample past 100,000 calibrating stars when combined with Gaia's parallax catalog. The result? 73. 5 kilometers per second per megaparsec, with an uncertainty pushed down to less than 1%, tighter than almost any previous local measurement, local or early universe. If that number holds up under continued scrutiny, it does something significant. It removes the escape hatch that Friedman's split results had briefly opened. Instead of one method disagreeing with 2 others, a combined, cross-checked, redundant approach converged on essentially the same higher number the JWST team had been defending for years. That matters because it directly narrows the list of possible explanations. If the discrepancy were caused by an overlooked measurement bias in one specific technique, a combined multi-method approach built to average out exactly that kind of bias should have pulled the number down, back toward the Planck prediction. Instead, according to this newest data, it didn't move. The tension held. So if it isn't a measurement mistake, what would it actually mean for physics if this tension is real and permanent? This is where cosmologists split into camps, and it's worth walking through the leading ideas. Honestly, because none of them is settled, and each one would mean a genuinely different universe than the one described in textbooks. One category of explanation is called early universe physics, meaning something about the conditions before or around the era the cosmic microwave background was formed needs revision. Proposals here include the existence of extra, undiscovered particles, similar to neutrinos, that would have slightly altered how fast the early universe expanded, or unusually strong primordial magnetic fields threading through the young cosmos, or a brief period where dark energy behaved differently than it does today, giving the universe an early nudge that current models don't account for. These explanations tend to fit the cosmic microwave background data cleanly, since they're specifically designed to adjust the early universe side of the equation, but they can create friction with other independent measurements, like the large-scale pattern distribution of galaxies across the universe, called baryon acoustic oscillations, which serve as another cosmic ruler entirely separate from both the CMB and the local distance ladder. Baryon acoustic oscillations are essentially fossilized sound waves from the early universe, frozen into the way galaxies are distributed across space at a characteristic distance scale, and they act as a kind of referee. Any proposed fix to the early universe has to still reproduce that pattern correctly, or it gets ruled out no matter how well it resolves the Hubble tension on its own. The other broad category is late universe physics, the idea that something about dark energy, the mysterious force driving the universe's accelerating expansion, has changed behavior more recently in cosmic history, rather than in the ancient past. Models here allow dark energy's strength to evolve over time rather than staying constant, which could produce exactly this kind of local versus early mismatch without requiring exotic new particles. These models tend to fit the local supernova and Cepheid data well for the obvious reason that they were built to, but they face their own tension with how consistently the CMB data matches a simpler, constant version of dark energy. Interestingly, some recent large-scale galaxy survey results from projects mapping how galaxies cluster across billions of light years have hinted that dark energy's strength might not be perfectly constant after all, a finding that, if confirmed, would lend real support to the late universe camp, though it remains contested and far from settled. Neither camp has a clean, uncontested win. Groups at institutions including SLAC National Accelerator Laboratory in Stanford have been running increasingly detailed simulations of how early primordial magnetic fields might behave, testing whether they can resolve the tension without breaking other established results. It's slow, careful, adversarial science. Every proposed fix gets checked against every other data set before anyone in the field will take it seriously, which is exactly why, years after Webb was supposed to settle this, it still hasn't been. Because both major methods rely on chains of assumptions, Cepheid physics, supernova consistency, the details of how the early universe evolved, astronomers have been racing to find totally independent ways of measuring H0 that don't depend on either the distance ladder or the CMB at all, specifically to act as a tiebreaker. One of the most promising is called strong gravitational lensing time delays, when a massive galaxy or cluster sits directly between Earth and a more distant, brighter object, often a quasar, or more recently, a lensed supernova. Its gravity can bend the background light into multiple distinct images. Because those different light paths travel slightly different distances, the images arrive at slightly different times. Measuring that time delay precisely, combined with a model of the lensing galaxy's mass, gives you a distance measurement that doesn't touch Cepheids, supernovae calibration, or the cosmic microwave background at all. Recent lensed supernova results using this method, including one project nicknamed Venus, have landed close to 73 kilometers per second per megaparsec, again favoring the higher, local universe answer. Another entirely independent approach uses gravitational waves, ripples in spacetime produced by merging black holes or neutron stars, first directly detected in 2015 by the LIGO and Virgo observatories. Because the physics of how a gravitational wave signal weakens with distance is precisely understood from first principles, these events function as what astronomers call standard sirens, giving a distance measurement that requires no calibration ladder whatsoever. The technique got its proof of concept in 2017 when LIGO and Virgo detected a neutron star merger whose light was also captured by dozens of telescopes around the world simultaneously, allowing scientists to measure both its distance from the gravitational wave signal and its recession velocity from the light. That single event produced an H0 estimate consistent with both camps at the time. Not precise enough yet to settle anything, but proof the method works. The sample size here is still small compared to Cepheids or supernovae, since detectable neutron star mergers with visible counterparts remain rare, but every additional detection adds another independent data point to check the other methods against. And next-generation gravitational wave observatories, currently in planning stages, are expected to make this one of the most powerful independent checks available within the next decade. The fact that gravitational lensing and gravitational wave sirens, two completely different physical phenomena, measured with completely different instruments, resting on completely different assumptions, both tend to land closer to the higher, local value than the CMB prediction, is part of why more astronomers have shifted over the past couple of years toward treating this as a real physical discrepancy, rather than a lingering calibration error waiting to be found. It's worth stepping back and asking why any of this matters outside of a physics conference. Here's the honest answer. The Lambda CDM model isn't just an academic framework. It's the working assumption behind essentially every prediction cosmologists make about the universe's past and future. How old the universe is, how much dark matter and dark energy it contains, how galaxies formed, and how the universe will end. The Hubble Constant is one of the model's most basic input numbers. If two independent, high-precision methods of measuring it genuinely disagree, and that disagreement can't be explained by measurement error, it means the model isn't just slightly incomplete around the edges. It's missing something structural, some piece of physics that changes how the universe behaved at some point between the era of the cosmic microwave background and today. It also touches something closer to home than it might first appear. The age of the universe itself, currently pinned at roughly 13, 8 billion years, is calculated using the same underlying framework that produces the lower early universe H0 value. If the higher local value turns out to be the correct one, and the model needs to be adjusted to accommodate it, that age estimate could shift as part of the same correction. So could our understanding of how much time galaxies actually had to assemble in the early universe, which loops this story back around to the very impossible early galaxy. Problem covered in earlier JWST coverage, It's entirely possible that the early galaxy puzzle and the Hubble tension aren't two separate mysteries at all, but two visible symptoms of the same underlying gap in the model. Several cosmologists have explicitly proposed exactly that connection in recent papers, though, like everything else in this story, it remains an open hypothesis rather than a settled conclusion. That's not a small correction. That's the kind of gap that, historically, has preceded genuine revolutions in physics, the kind of anomaly that eventually gets a name, a mechanism, and a Nobel Prize attached to whoever finally explains it. Nobody currently knows what that missing piece is. Every serious proposal on the table, extra particles evolving dark energy, primordial magnetic fields, remains unconfirmed, contested, and actively being tested against new data as it comes in. So here's where the real story leaves us, without any invented signal, without a hidden message, and without a shattered universe collapsing into the Matrix was a lie. Two extremely careful, competitive, well-funded teams of scientists have spent over a decade measuring the same fundamental number using completely different methods. And instead of converging as instruments improved, the gap has held firm and, if the newest 2026 data holds up, hardened further. James Webb was supposed to be the tool that finally closed this question. Instead, by ruling out the leading mundane explanation at 8 standard deviations of confidence, it did the opposite. It confirmed the tension was real and handed the problem back to theoretical physicists to actually solve. That's not a cover-up. It's not evidence of anything artificial or mystical. It's a genuine, unresolved crack in the best model of the universe we've ever built, playing out in public, across published papers you can search for and read yourself right now. If you want the primary sources, search for Adam Rees and the H0ES collaboration's Cepheid papers, or Wendy Friedman's Chicago Carnegie Hubble program results, or the 2026 H0 Distance Network release. All of it is real, all of it is public, and none of it has a final answer yet. It's also worth remembering that this wouldn't be the first time a stubborn discrepancy in astronomy turned out to be the doorway to something enormous. In the late 1990s, 2 independent teams studying distant supernovae found the universe's expansion wasn't slowing down under gravity the way everyone expected. It was speeding up. That anomaly, just as confusing and just as resisted at first, eventually became the discovery of dark energy itself and earned its discoverers the Nobel Prize in Physics. Nobody is promising the Hubble tension resolves into something that dramatic, but the pattern, a small, persistent, hard-to-explain-away discrepancy, refusing to disappear no matter how good the instruments get, is exactly the shape that past scientific revolutions have taken. That's what makes this worth paying attention to, even without a single invented headline attached to it. Which side do you think is going to giz? The early universe or the late one? Or is there a third explanation nobody's found yet? Tell me what you think is missing from the model in the comments. And if you want to know the moment this actually gets resolved, because eventually it will, subscribe. Because when someone finally cracks this, it's going to be one of the biggest physics stories of the decade.